All right, so we're going to look at the molecular orbitals for linear water. So the coordinate system we're going to use is the board is going to be the ZY plane. The oxygen atom is at the origin of that coordinate system. The hydrogen atoms are right on the y-axis, and Z would be coming in and out towards us. So the first thing we want to do is actually look at, classify the atomic orbitals that we're going to use to see if they're either even or odd. So the first one that we're going to use is the hydrogen 1s combinations. And make sure we do this even or the odds. Now, so there is the even combination of the hydrogen, it's just where they're the same phase. The odd combination would be where one of the hydrogen 1s orbitals is the one phase and the other is the other phase. So in this case, we're looking at red and blue. Another one we have to work with would be the oxygen 2s. Now, oxygen 2s would just be a sphere at the center, the ZX. So if we turn that 180 degrees, we're going to see exactly the same thing. So that one is one of the odd combinations, or sorry, even combination. The oxygen 2pz would be another one. So if we want to draw that one up here on the screen, it's a p orbital, so one phase is coming up, the other phase is going down. And if you spin that 180 degrees around the z-axis, you're going to get the same thing. The red on top, the blue on the bottom. So this one is also an even. The other one that we have to contend with would be the 2py on the oxygen. Let's draw that one on our coordinate system. So that one would have blue phase coming out on one side, red phase coming out on the other side. So if you flip that 180 degrees around the z-axis, you get the opposite of what you started out with. So that one is going to get classed as an odd. And then lastly, the other one that's a little bit tougher to see is going to be the last remaining oxygen 2p orbital. And that's the 2px. And that one's going to be coming in and out of the board. So if you think about this, if you're looking at it straight down into the board, you would see, for example, the blue part of that 2p x-axis. If you rotate around the z-axis 180 degrees, what you're going to see is the other part of it, which is the red part, which means that is also an odd. Now, so we're going to stick with the rule that evens mix with evens and odd combine with odds and see what kind of combinations we can get. So the even combinations. So let's do the simple ones. So let's start the coordinate system here. Here's the oxygen. And there are hydrogens. So let's start with our even hydrogen configuration, like that. And let's say we could mix that with the oxygen 2s orbital, which is the other even one. So that's just basically going to be a larger circle. So here we've got areas where they overlap. So just fuse them together. So that would be the additive combination. You've got increased electron density around both. So this would be the bonding configuration. The other way that you would combine these two, this would be the same set, if they were not of the same phase. So this would be, for example, oxygen 2s minus the even hydrogen combination. What would that look like? Well, we still have the oxygen 2s, except now the hydrogen 2s's are the other phase, the other color. So whenever you have region of opposite sign overlap, you separate the two. And so now note that here we've now created a node in between each of the oxygen-hydrogen bonds. So this would be the anti-bonding combination that you would get from the evens. Let's look at the odds now. So the odd combination would be, for example, the 2py. And then the odd hydrogen combination. So that, and you could combine them in one of two ways. This way, where the phases match up. So this would be oxygen, what's the hydrogen 1s combination? This would be a bonding combination. And the other way that these could line up is if they were out of phase. So I'm going to keep the oxygen the same, but change the hydrogens. Now the overlap is of opposite color, opposite phase. So you separate them. And here we also have two nodes that are between the oxygen-hydrogen bond. So this is the anti-bonding combination, but this is still the oxygen 2py plus hydrogen 1s. Now the one interesting one that in this shape actually goes from bonding to non-bonding is one of the even combinations, and I'll do that one separately here. And that is the hydrogen 1s along with the 2pz. Now in the bent geometry, these hydrogen orbitals are a little off-center. They're not right on the y-axis. They're actually down here. So they'll either constructively add with this or destructively add depending on what sign or the way that that p orbital is. But in this case, no matter how you orient these, there's going to be non-bonding interactions because each of these s orbitals is going to overlap with as much of the same color or the same phase as the opposite phase. So this one actually becomes non-bonding, which is different. Than what we saw in the linear structure. So, and this is one of the reasons why the water is bent and not linear. So this is how you do the crude molecular orbital analysis for linear water, or any linear AH3 molecule, or AH2 molecule, sorry.